Welcome to class 13 in thermodynamics. We are starting chapter 4, and this one's with control volume, conservation of mass and energy, and the chapter is entitled, there you go, Energy Analysis for a Control Volume. We have a couple different control volumes represented by the dashed line, and we usually use that to as a boundary, and we see what crosses the boundary into the control volume, and we keep track of that, both the mass and the energy. Some control volumes can store mass, and therefore they can also store energy. These are usually transient types of things. They're making changes with time. So we'll see pretty soon that we kind of discard that, and typically we'll look at a steady state situation. So let me think. I want to change over to my document camera here and go with those notes this way right here. Okay. So because I've removed some of the text in here, I wanted to describe it. So this conservation of mass. In the idea up here, right, where they have a control volume where you could see that this tank will start to fill, and so mass is accumulating in here. And also, if you decided to draw the line right here where this piston would be moving as well, there could be like the displacement within there would change, the volume would change. So we have various things that would maybe accumulate, right? So we have the mass that could accumulate, and as an extension, the energy within there would accumulate. So we want to, for the time being, say the mass of the control volume as it changes with time is going to be equal to the summation of all the masses that are coming out. All the masses coming in. Right? That would be the convention, the sign convention, minus the summation of all the mass flows coming out. Right? So out is negative. It says it right above there, the change. And quite often this will be zero when we have a steady state, right? So this term right here represents some type of storage. Either it's accumulating or it's depleting. Another concept, so there's a separate concept. There's the conservation of mass, which I might start calling the COM, the COM. All right, so we also have, we also do this mass, we'll often do a mass flow rate. Well, we have a partner, his buddy, we'll often do a volume flow rate. And the volume flow rate, just as a simplification, a lot of times we're going to, whereas we know that the volume through a pipe or a duct or whatever, it can vary. In fact, it's maximum right here in the center, and it theoretically comes down to, I guess actually even practical, it comes down to zero right there at the very, very inner part. We call that the no slip condition in fluid mechanics, just so you know. So the velocity does change throughout the section. So quite often what we'll do is we'll use an average right there. So a volume flow rate, which I'm going to use the naval architecture volume with the cross through there to distinguish it from the velocity. We could find that by taking the integral across the area for individual little tiny areas. Right, so we have little different areas and find the velocity at each area right there so that we could get the entirety. And a lot of times I think the book decides to call that the local velocity. So at each of these different spots, right? So we would find different little tiny areas right there and then find the velocity. And so that would be the total volume flow. Most often what we're going to do though is we'll take the average velocity times the area right there, and that'll give us a volume flow rate. And I often think about it as like taking, if you took a volume, if you took an area right here and you moved it, right? So you kind of swept it right there, you would create a volume for this distance, but now what we're doing is we're multiplying it by velocity. So it's not just a distance, it's distance per time, and that's how much of a chunk of something is going per time through a duct or a pipe. And to get over to the mass flow rate from that, you could just take the density and multiply it by the volume flow rate. Or, because we do it so often with our specific volume, we could just take this volume flow rate and divide it by the specific volume, and we would get the same thing. So, and then, just to reiterate here, we could take the average velocity times the area and divide it by the specific volume. And you can see why, I've decided to use the naval architecture V here, because it's confusing to have these different V's. I decided velocity should be uppercase V in this course, but in dynamics, I usually make it like a cursive V. But just to try to keep things separated right there, it gets confusing. So the most typical equation that we'll use for this is to have this guy right there. So I wrote a lot of equations, and but right here, and I'll leave off the average because we'll just assume, right? So this is very commonly done. Anything I want to say? No, we'll make another video for the example. No, this example's way too easy. So we'll go ahead and I'll be a liar. I lied. Yeah, so this is a really easy example here, where it says the air is flowing in a 0.2 meter diameter pipe at a uniform velocity of 0.1 meters per second. The temperature is 25 degrees Celsius, and the pressure is 150 kilopascals. Determine the mass flow rate. Well, see, they don't say anything about density, so that's the ideal gas law. So we will go to table. I think it's A5, and air, we almost should have this memorized by now. We have 0.287 kilojoules per kilogram degree Kelvin, right? And so we could use the ideal gas law of PV equals MRT, or PV equals RT if you turn that into specific volume. So we could find the specific volume by multiplying R times T and dividing it by P. And just to keep my units square, I like to turn this into Newton meters per kilogram. That's the way my thought process goes. I take this, and it's 25 degrees, so we want to go 25 plus 273. You can always remember to use absolute temperatures. And then I divide it by 150,000. Now I recognize that's sort of silly because I multiplied this by 1,000. I got rid of the kilojoules right there, and then I also got rid of the kilopascals right here. So I'm doing it, but they will cancel out. It would be the same thing. You could just use 0.287 and 150 on the bottom, but this is my nod towards how the units work out. So I get 0.5702 cubic meters per kilogram. And then we want to find the area. Do I need the area? Yeah, we do, because the equation I'm using, as I mentioned in the previous slide, was just the volume times the velocity times the area, which would give me the volumetric flow rate divided by the specific volume. So I need the area. So I'm going to go pi over 4d squared, and that's going to be 0.2 in there, and we get 0.03142 square meters. And so the mass flow rate is going to be 0.1 meters per second times our area, 0.03142 meters squared, divided by 0.5702 cubic meters per kilogram. And then looking the thing out, you'll see the seconds are going to stay there, but we have a square meter and a meter, so that meter cube, okay, they all works out, and that kilogram comes back to the top. So we get 0.00551, good enough, kilograms per second. Let's write it out again. Almost want to make, now, we could almost go grams per second if you wanted to, but I usually use kilograms. So 551 kilograms per second. And that's enough of a video. So that was example 4.1. A little easy, but you want to get used to using or thinking in terms of this equation right there.